So actually we're adding a section to our Notepack that I forgot to include. Will definitely be included next year, which is, we're going to call it 6-2A, because we're solving systems algebraically, but now we're solving systems that have 3 variables instead of 2. So let's get to work on that. So we will have practice on this, and you will just need to attach these notes inside your Notepack between section 6.2 and section 6.3. So a linear equation in 3 variables, x, y, and z. So now instead of just an x and a y, we also add a z, and has the form. If you wanted to do a standard form of that, it would be something like ax plus by plus cz equals d, where a, b, c, and d are coefficients. Just straight numbers. Okay. And when you give the answer for that system, you would have now 3. It's actually a 3-dimensional answer instead of a 2-dimensional answer. So, and I'll show you in class, we'll actually graph one of those, and I'll show you what that would look like, a system. Pretty hard to do on paper because paper is 2-dimensional. We can do it on a computerized graphing program, and you can see what a 3-variable system would look like graphically. So when you list your answers for those, you will need to list them as 3 coordinate points instead of 2. So it will look like x comma y comma z. And the important thing to remember is that it must be a solution to all 3 equations. So all the rules are the same as with 2-variable systems, and the only difference now is we've got 3 variables. So let's just try checking to see if the given solution is in fact a solution to the entire system. It must satisfy all 3 problems, all 3 equations in order to be a solution. So we're just going to check these one at a time. 1 is our x value, 4 is our y value, and 2 is our z value. So I'm going to check the first one, just plugging in our values for x, y, and z, and verifying that they equal the standalone value on the other side. So we get -2 minus 4 plus 10. Well, -4 and -2 is -6 plus that is 4. So that does not equal 12. So right off the bat, we know that that does not satisfy that system because it must satisfy all 3 equations. It does not. First one right off the bat, it doesn't satisfy. So let's check the other one. So on number 2, we have 7, -1, and 0. So -4 times 7 plus 6 times -1 minus 0 should equal -34. It's -28 minus 6 minus 0 does equal -34. So our first equation checks out. Second equation would be -2 times 7 minus 5 times -1 plus 8 times 0 should equal -9. So -2 times 7 is -14, -5 times -1 is +5, plus 0 does equal -9. So the second equation checks out. Finally, 5 times 7 plus 2 times -1 minus 4 times 0 should get an answer of 33. 35 minus 2 minus 0 is 33, and the third one checks out. So if all 3 equations check out, then yes, that is a solution to the system. Okay, so pretty much the same as the others. So when you're actually getting down to solving them, there's kind of a process that I want you to do. And I think that elimination is most commonly used because usually you have some kind of coefficient in front of the x, y, and z. So I want you to think about a pattern that kind of looks like this, where you're starting with 3 variables, getting down to 2, eventually solving for 1, and then working back to 2, and eventually back to 3. So I just want you to kind of visualize that pattern in your head as you're solving these. So here's your steps. So the first thing you're going to do is label your equations. It's the easiest thing to do. You can either label them A, B, C, 1, 2, 3, whatever you would like to label them with. You're going to choose 2 of the equations. So let's say, for example, you pick equations A and B. Then the next thing you're going to do is you're going to choose one of the variables to eliminate. So you're going to say, okay, I'm going to choose the first 2 equations, A and B, and I'm going to eliminate my x's first. And then you're going to go ahead and do that. Then you'll end up with only y and z in those 2 equations, giving you a new equation to use. Then you're going to repeat that process, say with A and C or B and C. and eliminate the x again. So you will have the same two variables left over. Now you're back to a two-variable system, which you've been doing, and those are easy to do. So let's go ahead and try one. You kind of need to see how these work. Okay, so on the second page of your notes, so you're going to label the equations as A, B, and C. Okay, and then choose a variable to eliminate. So let's just choose to eliminate x. Okay, we can do that. So let's write our equations that we've got. So our A equation is x minus 2y plus z equals 0. And our B equation is x plus y plus 2z equals 7. So let's just start with that. I'm not even going to worry about this second equation yet. All I did was transfer these equations over here. So I'm going to eliminate the x's. So we know in order for them to eliminate, they have to be opposite signs. Currently, they are not. So to me, the first equation is easier, and I'm going to multiply that entire equation by -1, which would make this negative x. Negative x plus x would be 0. My x's would be eliminated. So I'm just going to simply flip the signs on all of these. Opposite of 0 is just 0, so that's convenient. Okay. So, well, I guess I could do that down here. So x plus y plus 2z, that B equation didn't change. And then when I flip it, I get negative x plus 2y minus z equals 0. Now when I put those two equations together, my x goes away. I have 3y plus z equals 7. So look what happened. Now I only have a two-variable system. Easy. That's what we did in 6-2. Not a problem. Now I need to repeat that entire process with a different pair. One of the equations can overlap. I just can't do B and A because that would obviously be the same thing. But A and C is a different pair. So again, transfer your equations over. And C would be 2x plus y minus 3z equals 5. And then in order to get that to eliminate, the opposite of 2x would be negative 2x. So I'm going to multiply that entire A equation by -2. So that'll give me negative 2x plus 4y minus 2z equals 0. And then I'm just going to transfer my C equation down. When you are working on these problems, you're going to hear me say it a lot, you must be extremely organized. The other thing you need to do is go back and check that you wrote the problem down correctly and check that your signs are correct. You're going to get really frustrated if way back here you made a mistake in this problem and you can't figure it out till you get all the way to the end and realize that you made a mistake. So at every step you need to be extremely organized and extremely tedious about checking your signs and making sure they're correct. Those are the two things that will get you in three-variable systems, is not writing the problem down correctly and not checking your signs as you multiply. So that's my advice to you. So now we have, sorry, the lights just flicked off in my room. Have a minute. There we go. Okay, so now negative 2x plus 2x cancels. I get 5y minus 5z equals 5. So now that I have that, now I have two new equations. Each have a y and a z. My x's are gone for now. So what's really going to happen is whatever the first equation is that you eliminate is going to be, or sorry, excuse me, let me restate that. The first variable that you eliminate is going to be the last one that you solve for. Okay, so x is going to be the last thing that I solve for when I get down to that step. All right, so I'm going to move my two equations over. So I have 3y plus z equals 7 and 5y minus 5z equals 5. And then I'm going to choose one of those to eliminate. To me, it's easier to eliminate z because I've got a positive and a negative, and I would just need to multiply this equation by 5. I'm going to move those over, so I get 15y plus 5z equals 35. And 5y minus 5z equals 5. I'm going to put those together. My z's eliminate. I get 20y equals 40. So my y equals 2. That's my set. So I can write that in there. Remember, this is going to be your x, y, and z. Sorry. And once I have that, I can use my 2, plug it into any of these equations to solve for z. So I'm going to go ahead and use the first equation because z is isolated already, so it's kind of easy. So 3y plus z equals 7. My y value I know is 2. So 6 plus something gives me 7, so my z equals 1. So that goes in the third spot in my answer. Now that I have a z and a y, what can I do? Now I can go back to any of my original equations, a, b, or c, doesn't matter. Plug in y and z and calculate x. So I'm going to go ahead and I'm going to use the second equation. Don't know why. Like it. So x plus y plus 2z equals 7. Well, now I still don't have a value for x. It was the first thing I eliminated, so it's the last thing I'm going to solve for. And my y value is 2, and 2 times my z value, which is 1, will give me 7. So x plus 2 equals 7. 2 plus 2 is 4. So I'm going to subtract 4 from that side, and x would equal 3. Now, I just used my b equation to solve, so I am going to check 3, 2, 1 as my solutions in A and C, just to double check. Checking one is great, checking all of them is better. So my A equation, my x value is going to be 3 minus 2 times my y value is 4 plus 1 should equal 0. And 3 minus 4 is negative 1 plus 1 is 0, so that checks out. Checking should be fairly straightforward and not difficult for you to do at this point. My second equation, my x value is 3, my y value is 2, plus 2 times my z value is also 2, and that should equal 7, and 3 plus 2 is 7, so the second one checks out. The third equation, 2 times my x value would be 6, my y value is 2, negative 3 times my z value would be negative 3, and that should equal 5. 6 plus 2 is 8, minus 3 equals 5, so that checks out. So I do know that that is a good answer, and I calculated it correctly. Okay, so I'm going to do number 1 at the bottom with you, and we're going to use that same process again. So the first thing I want you to do is give your equations, designate them somehow so that you know which one you're talking about. When you're doing this, you can look and see which variable looks like it might be the easiest to eliminate. Tends to be the one that doesn't have any coefficient in front of it. Might be easier. They're really not difficult, any of them. So I'm looking here, and all of my x's have coefficients, all my z's have coefficients. Y has a negative 1, which might be the easiest to use. So let's just choose y this time. So I'm going to choose A and B first. So I have 3x plus 2y plus 4z equals 11. And I have 2x minus y plus 3z equals 4. So in order to eliminate the y's, I would have to multiply this equation by 2. And I'm just going to write it right below here. So I would get 4x minus 2y plus 6z equals 8. Now I no longer need this equation. Now I can just add my equations together. My y's are going to eliminate, which is what I wanted. And I have 7x plus 10z equals 19. So that's one of my equations I'm going to have in a second. Then I'm going to repeat that process again. And I'm going to have let's pick B and C. That's fine. Doesn't matter as long as it's not the same pair. So 2x minus y plus 3z equals 4. And 5x minus 3y plus 5z equals negative 1. So since I still have to eliminate my y's, if I eliminated my y's in this pair, I need to eliminate my y's in this pair. Well, the opposite of negative 3y would be positive 3y. So that means that I need to multiply this equation by negative 3. Negative 3 times negative y would give me positive 3y. And again, I'm just going to write it right below. So I tend to write them right below here and then cross them out when I'm done. You can do it whichever method you choose. Negative 3 times 2x would be negative 6x. Negative 3 times negative y is positive 3y. Negative 3 times 3z is negative 9z equals negative 12. Now that I've found an equivalent equation, now I can just add them up. Negative 3y plus 3y eliminates, which is what I wanted. 5x minus 6x is negative x. 5z minus 9z is negative 4z. And negative 1 minus 12 is negative 13. So now I've got two variable equations. I have basically a two variable system, and now I can go through and solve. So let's kind of give yourself a line so you can kind of see where we went from 3 variable down to 2 variable. So I've got 7x plus 10z equals 19, and negative x minus 4z equals negative 13. I'm going to go ahead and eliminate the x's because I can easily manipulate that second equation to make that a negative 7x just by multiplying by 7. So I'll get negative 7x minus 28z equals, would that be 91? Negative 91. Don't need that equation anymore. My x's cancel. 10 minus 28 is negative 18z. And 19 minus 91, I believe, is negative 72. That'd be right. 9 plus 2 is 11. Carry the 1. 7 plus 1 plus 1 is 9. There we go. Divided by negative 18. So my z value would equal 4. Right at the top, make sure you put your parentheses so that you remember that you need 3. Now you kind of work your way back up the chute. So now you go back to your two variable equations. Now you have a z value that you can plug in here and solve for x. I'm going to use the first equation because there's no negatives there, and to me that's easier. So I would have 7x plus 10 times my z value of 4 equals 19. 7x plus 40 equals 19. 7x equals negative 21 because I had to subtract that 40 from both sides. So x would equal negative 3. This is a big place to keep an eye on your signs. Remember what I said, that whatever your first variable is that you eliminate, it's going to be the last one that you solve for. That's exactly what's going on here. So I'm going to now, I can go back to any 3 of these equations. Again, I tend to use the one that doesn't have any negatives in it. That's just what I do. You can choose any of them. They will work for all. So I'm going to use the A equation. So 3 times my x value is negative 3 plus 2y plus 4 times my z value is 4 equals 11. So I've got negative 9 plus 2y plus 16 equals 11. 16 minus 9 is 7. So I need to subtract 7 from the other side. Those go away. Get 2y equals 4. So y equals 2. So in theory, my solution should be negative 3, 2, and 4. Of course, I'm going to check that to make sure. So since I used the A equation to solve, I'm going to use B and C to check. So 2 times my x value of negative 3 minus my y value plus 3 times my z value of 4 should equal 4. Negative 6 minus 2 plus 12, so that's 12 minus 8, should equal 4, and it does. Using the third equation, 5 times negative 3 minus 3 times 2 plus 5 times 4 should equal negative 1. Negative 15 minus 6 is negative 21, plus 20 equals negative 1, and that checks out. Okay. For the sake of room, I'm actually going to do number 2 on the back, and I'm going to again play music while I'm doing this. Kind of liking adding that into so I'm going to do this on the back. You can do it. I highly suggest when you're doing these, give yourself plenty of room. Make sure that you have plenty of paper, binder paper to do this on, because you need the room to spread out. So even if you have to add another piece of paper to your notepad, do it. It's not a big deal. All right, hang on one sec. Okay, really quickly, I also want to mention that you can have no solutions in 3-variable systems. So if you ever end up with any number equals some other number. All of your variables have been eliminated. So for example, you got through all your problem and then you had 0 equals 4. So that's never true. And that's going to be a no solution. It is possible to have no solutions in 3 variable systems just like it is in 2 variable systems. I just want to get that out there. May run into that. Probably will run into that at some point. So I just want to make you aware of that. All right. Same steps, A, B, C. Enjoy the music and watch me work. See, we ran right into it. So 0 equals 8. Is that ever true? Never true. So this is actually an example of a no solution 3 variable system. So that was quicker than I thought. I didn't even get a time to play music for you. So when that happens, when all of your variables on the left-hand side will cancel, even one of them, if you ever get to 0 equals another number, that's never true. So that would be a no solution. So glad we ran into that right off the bat. Okay, so just like in 2 variable systems where you have 2 options of elimination and substitution, substitution is also an option for 3 variable systems. Again, it's only when one of those variables is easily isolated. Okay, so if it's not easily isolated, it's always got a coefficient in front of it, I wouldn't deal with substitution if it were me. I would just go with elimination. So you're going to rewrite one of the 3 for substitution. You're going to rewrite one of the 3 given equations by solving for one variable. Get one variable isolated by itself on one side of the equation, the other 2 variables on the other side, along with a constant if there is one. Substitute the expression found in step 1 into the other 2, because by doing that, you will eliminate, you're making change, right? So you will eliminate that variable in the other 2 equations. Now you have a 2 variable system that you can solve, and then you can go right back into what we've done before. So again, you're going to label them A, B, C. Really helps with the organization of this. Okay, and choose a variable to isolate. So let's say we're going to isolate X. X is pretty easy to isolate. It's sitting there by itself. So if we do that in B plus 3y, this is a big time to remember. Anytime you move something to the other side of the equation, it's going to flip its sign. So the 3y and the z are going to move. So when they move, they're going to change signs because we have to move them over there by doing the opposite. So in this case, x would equal negative 3y plus z plus 1. Now that we have that, we can substitute this amount. Let me get a different color highlighter here. We can substitute this negative 3y plus z plus 1 wherever we see an x in the other 2 equations. Okay, we can replace it. So in our A equation, we have 2, and instead of x, we're going to put in negative 3y plus z plus 1 minus y plus z equals negative 9. This is why I think substitution method is a little bit more cumbersome. It's not really my favorite, but that's okay. We can go ahead and multiply that out. So 2 times negative 3y is negative 6y plus 2z plus 2 minus y plus z equals negative 9. I'm going to go ahead and move that constant over to the other side by subtraction, so that would be minus 2. Then since I'm on one side of the equation, if you need to put that line in there to help you, you need to do that. Okay, so we moved the 2 over. Z and 2z I'm going to put together. So I've got 3z. And I like to cross things out as I go. Negative 6y minus y is negative 7y. So what you really have to remember is that you have things on one side of the equation and the other side of the equation. The goal is that you end up with two variables on one side and your constant on the other side. So in this case, we get negative 7y plus 3z equals negative 11. Okay? You're going to repeat that process with the c equation. So you have 3x, but for x, I'm going to plug in everything that x is equal to. So negative 3y plus z plus 1 plus y, and just bring the rest of the equation over, plus y minus 2z equals negative 12. Okay, and then multiply out, so you get negative 9y. I'm going to kind of put a line in there so it's easier for you to see the difference. Plus 3z plus 3 plus y minus 2z equals negative 12. I'm going to push that 3 to the other side by subtraction, so that's gone. Negative 9y plus y is negative 8y. 3z minus 2z is just z. And negative 12 minus 3 is negative 15. So that's my second equation. Plus z, let's just bring it down, equals negative 15. Okay. Now I've got my two equations. Let's bring them down here. Negative 8y plus z equals negative 15. Now you're back to a two-variable system. Should be easy at this point, hopefully. We're doing this by elimination. So even though you use substitution up here, that doesn't mean you have to use substitution down here. Could you? You certainly could, because you could make the z isolated by moving the negative 8y over and making it positive. Again, I prefer elimination. I think it's easier. So I'm going to eliminate my z's, so I'm going to multiply this second equation by negative 3. So I would get 24y minus 3z equals 45. Once I do that, I don't need that equation anymore. Now I'm just totaling up. 3z minus 3z cancels. That's what I wanted. 24y minus 7y is 17y. And 45 minus 11 is 34. So my y value is 2. Put that over here. Now that I have a value for y, since I have y and z in this system, I can go ahead and plug that in. I'll go ahead and use the first equation. Doesn't matter. I'll use the first equation to solve and the second equation to check. So negative 7, my y value is 2, plus 3z equals negative 11. Negative 14 plus 3z equals negative 11. I've got to add that 14 over. So I get 3z equals 3, so my z value equals 1. Now, again, like I said, whatever variable you eliminate first is going to be the last one that you solve for. So now that I have that, I'm going to go ahead and use since I already isolated the x, I can actually use this equation right here. So I'm going to use my isolated one because then I don't have to move anything around. And my y value is 2. My z value is 1 plus 1. So that should give me negative 6 plus 2, which would be negative 4. So my x equals negative 4. Of course, I'm going to check my answers. Since I used that b to solve, I'm going to check in a and c. So my a equation, get that out so you can see it, is going to be 2 times my x value, which would be negative 8, minus my y value, plus my z value, which is 1, and that should equal negative 9. Negative 10 plus 1 is negative 9, so that checks. Now I'm going to check c. 3 times my x value of negative 4, plus my y value of 2, minus 2 times my z value of 1, should give me negative 12. Negative 3 times, did it again. 3, if you don't move enough, then the light automatically turns itself off, but I'm not done yet. So 3 times negative 4 is negative 12, plus 2 minus